Let's go over this example of four charges. It's an example of Coulomb's law in two dimensions. So we're going to consider four charges. They're arranged in a square pattern. We're going to calculate the direction of the net force on the top left charge, this Q1, right? So we're interested in the force on Q1 due to the other three charges. And the trick we're going to play here is, although we technically don't have to, conceptually it is easier for us to think of it if we think of the other charges as being glued in place, right? Uh, Again, technically it's okay if they're not, but to make life easier conceptually for us, imagine that all the other charges are glued in place so that they can't move. But Q1 is free to move, and we're asking what force is on it. Okay, so before we dive in, we want to take a step back and think about what we're trying to figure out, right? The answer is that we're trying to calculate the electric force on a charge. And obviously right now we've only got one topic into this course, so the strategy is obvious. But when we add more and more possibilities, we need to take a step back and think about the best way to attack any particular problem. Now, in this case, what tools do we have to calculate a force on charges? We have Coulomb's law, right? So we're going to be utilizing Coulomb's law. But if we take a look at the question in detail, we're asked for a net force, right? And a net force is achieved by calculating individual forces and adding them up with vector addition, right? So that suggests a strategy of looking at each of these individual charge pairs, right, between Q1 and Q2, and calculating a force between them, Q1 and Q3, calculating a force between them, and Q1 and Q4, and calculating a force between them, and then adding them all up, right? And that's the beauty of these linear forces, is that you can calculate the force due to this charge on this charge as if these guys did not exist. And then when you move on, you say, now I'm going to pretend this one doesn't exist, and that the only one that exists are the charge I'm interested in and the charge that is affecting it at this in this kind of mental strategy. Then we pretend these two don't exist, and there's just these two, and we calculate the force on 1 due to 4 as if 2 and 3 didn't exist. And then at the very end, we add all of them up, and we end up with the exact same answer as we would have gotten if we had considered all three simultaneously. All right, so that breaks it down and makes it nice and easy for us. So what information do we have, right? We're given the separation between Q1 and Q2, as well as between Q1 and Q4, but we don't have directly the separation between Q1 and Q3, right? We don't have R31, right? This is 1 meter, this is 1 meter, but this is not labeled. So that's kind of now a missing piece of information, because if we had all the charges and we had all the distances, then we would be able to calculate the individual Coulomb's law for each one of these pairs. We have all the charges, we have 2 of the 3 distances, so we're missing a piece of information. So this becomes like a 2-step problem. It's a trivial 2-step problem, but nonetheless, we'll remain kind of pedagogical at this point. And let's say that we require one more piece of information. So we have a new goal. Our new goal is to find R31 or R13. Sorry, it's labeled R31. So how do we find R31? Well, we can use Pythagorean's theorem, right? We know this basically forms a right triangle, 1 meter on this edge, 1 meter on this edge, and this is the hypotenuse. And the hypotenuse is what we're interested in, right? So a squared plus b squared is equal to c squared. And from that, we can calculate the unknown R31 as square root of 2, right? 1 squared plus 1 squared, square root of the whole thing is 1.4 meters. Okay, so again, I think it's a good idea to list all the known quantities plus the one we've now just calculated, right? And the next step is going to be calculate the magnitude of each one of these force pairs individually, right? So first, the force on charge 1 due to charge 2. Plug in our Coulomb's constant. Charge 1 is 1 microcoulomb, 10 to the minus 6. Charge 2 is plus 1 microcoulomb as well, and they are separated by 1 meter. And plugging in the numbers into your calculator, you get 9 times 10 to the minus 3. Okay, the magnitude of force for 1 is also 9 times 10 to the minus 3 because it's also 2 positive when charge is separated by 1 meter. Finally, R31 across this diagonal here, these are two charges that have opposite signs. So now we have charge Q3 is equal to minus 1 times 10 to the minus 6, and Q1 is 1 times 10 to the minus 6, plus 1, right? So we have this one and we have this one. We put in those two charges, and now the separation between them is this R31 is 1.4 meters. Right? So we plug in those numbers and we get 4.5 times 10 to the minus 3. And it makes sense that this is smaller because this distance is larger, they're further away, they don't feel each other's effects as strongly. And the charges are still the same as the others. It's just the sign is flipped. Okay, but again, these are all vector quantities, so the magnitude is not enough. We also need the direction of each of these forces. So let's look at the directions of each one. Right. The force of this one due to this one, we pretend this one's glued down, we're interested in how this one will be pushed due to the charge on this one. Well, these two are the same, and like charges repel each other. So this guy is going to be repelled by this one, so it's going to shoot straight up, right? So it points straight up. And if you look at the way we can do our angles in standard convention, remember 0 degrees points to the straight to the right, and then positive angles are counterclockwise. So this will be 90 degrees, positive 90 degrees. For the negative charge, this is, again, assuming that the other two charges don't exist and the negative charge is glued in place, then Q1, the one we're interested in, will be attracted to Q3. So that means it's going to pull this way along the line that connects the centers. And that turns out to be, since this is 1 and this is 1, it's going to be 45 degrees. Right? So, but because it's being pulled in this kind of southeasterly direction, we could either call that something like 315 degrees, or more easily, we can call it minus 45. Right? So we'll label this as minus 45 degrees. Finally, the third vector is when we consider the only two charges to be there as Q1 and Q4. Q4 is glued in place. Q1 is going to feel repulsive force, which means it's going to want to push this way, which is in the negative x direction, which is 180 degrees over here. All right. So then, now that we've gotten each individual force, each individual force and their directions, what we're going to do is we're going to add them up. Now we could again do this pictorially, but to be mathematically accurate, we'll do this with the algebraic method. Sorry, so we'll use it with the algebraic method. And what that means is we take the x and y components of each of these forces, right? So we'll look at the first force, the force 2,1. It's pointing straight up, so clearly the x component, which is also the cosine of the angle between them, is 0 degrees. Right? Cosine of so the component along the x-axis is 0 because it's pointing straight up. For the 3,1 force, it's pointing down here at minus 45 degrees, so it does have an x component, right? Cosine of minus 45 degrees is 0.707, so it's going to be like 70.7% of this full value is going to be pointing along the x direction, and it's positive because you can see that the component along the x direction is pointed to the right. X component of minus 180 degrees is the full thing, but it has it's a negative sign, and cosine of 180 degrees gives you minus 1. Right, so then finally we can add up all these individual x components, right? 0.707 of F3 minus magnitude of F4. Right? Plugging in the numbers, we get minus 5.8 times 10 to the minus 3 newtons in the x direction. That's the x component when you add up all the individual forces. We do the same thing with a y, and I won't belabor it because you can easily plug in the signs for all these angles. And plugging in the numbers, we get plus 5.8 times 10 to the minus 3 newtons. Right? So we have something that's going negative in the x direction, but a net positive in the y direction. Right? So it's going to be going kind of at 45 degrees this way because it's got equal amounts of x and y going negative x and positive y, so it's going to push this way. And that makes sense because if you got these big push going up and a big push going to the left and a small pull down and to the right, then these guys are going to dominate over this one and it's going to end up going this way, just not as strongly as if this guy, if compared to if this guy didn't exist. Okay, but quantitatively, we can get the actual magnitude of the net force by taking the x and y components and using Pythagorean's theorem on it again, right? X squared plus y squared, square root of the whole thing, will then give us the magnitude of the full net force on Q1 due to these other three charges. Right? And that obviously points up and to the left, as we said. If we want to find the angle of this vector, this final vector, we can take the arctangent of the y component over the x component. Plugging in the numbers, we get 45 degrees, right? But we got to be careful here because tangent's one of those numbers where you get the same number depending on what quadrant for two different quadrants. So we got to take a look at this and be careful. What we calculated was for 45 degrees with these two positive numbers in. You got to be careful with calculators on how you do this. So it's good to have a drawing, right? We see that it's 45 degrees, but that's really when you have this and this, right? And so the angle that you've measured is here, but we know it's pointing to the up and to the left, and that positive 45 degrees, according to our map back here, would be pointing up and to the right. So in order to get the actual correct angle, we have to realize that theta net is actually 180 degrees minus this little thing that we calculated right here, this angle, right? And so 180 minus 45 gives you 135 degrees. And so our final answer is that the net force is 8.2 times 10 to the minus 3 newtons at an angle of 135 degrees relative to the x-axis.